Hi, hello friends, welcome back to our channel. This is Bhaskar Bora. We are discussing 10th class first chapter real numbers. So in that up to now we discussed Euclid division lemma and using Euclid division algorithm how to find the HCF of given two numbers, and also we explore the properties of real numbers using Euclid division lemma. Now today in this video we are going to discuss fundamental theorem of arithmetic. So what is the fundamental theorem of arithmetic? Let us understand this by taking some examples. Let us consider a number 24, which is the composite number. So we know that a composite number is a natural number which has more than two factors. So now 24 is a composite number. So let us factorize this number. So 24 can be written as 2 into 12. Where the 2 and 12 are the factors. Now here in 2 into 12, 2 is the prime number and 12 is the composite number. So 12 can be further factorized. So let us factorize it again. The first factor, write the 2 as it is. Then by factorizing 12, we get 2 into 6. Now we get 2 into 2 into 6. Now here the 6 is again the composite number. So let us factorize it again. So by factorizing 6, we get 2 into 3. Therefore altogether we get 2 into 2 into 2 into 3. Now in the last step, we have all the prime factors. And we know that this method is known as prime factorization. So what is the prime factors of 24? The prime factorization of 24 is 2 into 2 into 2 into 3. Now similarly, let us factorize the same 24 by taking its another pair of factors. Can you tell me the another pair of its factors? I think you say the pair of factors as 3, 8 or 4, 6. Let us take the pair of factors 3 and 8. So 24 can be written as 3 into 8. Now in this 3 into 8, 3 is the prime number and 8 is the composite number. So we can factorize 8 further. Let us factorize it. What can we write? 3 into 8 can be written as 2 into 4. Now we get 3 into 2 into 4, where 4 is again composite number. So we can further factorize it. So on factorizing it, we get 3 into 2 into 2 into 2. So what we get? The prime factorization of 24, that is 3 into 2 into 2 into 2. Now let us do again the prime factorization of 24 using another pair of factors, that are 4 and 6. So 24 can be written as 4 into 6, where both 4 and 6 are composite numbers. So let us again do factorization. We get 4 can be written as 2 into 2 and 6 can be written as 2 into 3. Now what we get? 2 into 2 into 2 into 3. Now in these three cases, the same 24 is prime factorized. Now in every case, we get the same prime numbers as its prime factors. Here we have 2 into 2 into 2 into 3, and in the next case we have 3 into 2 into 2 into 2, and in the next case we have 2 into 2 into 2 into 3. So in all these three cases, we have the same prime numbers as the factors of 24, except their order. So that means 24, when expressed in its prime factors, we can express it in one and only one way. That is, we can write the same prime numbers as its factors, except their order. Now let us take one more composite number. Suppose let us consider 36. Find its prime factorization by taking its different pair of factors and observe whether you get same prime factors or not, except their order. So here 24 and 36 are the composite numbers, and when we expressed them in their prime factors, we get the same prime numbers as their prime factors except their order. So like this, every composite number can be factorized using prime factors. And this factorization is unique. That means we can express every composite number with the same prime numbers. Apart from the order, in which the prime factors occur. This gives us the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic says us that every composite number can be factorized or expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So that means from this we can understand that every composite number can be factorized to its prime factors, and that prime factor is unique. That means we can express that composite number in one and only one way as its prime factors, except their order in which they appear. So using this fundamental theorem of arithmetic, we can explore the properties of real numbers. So let us consider one problem. Is 7 into 5 into 3 into 2 plus 3 a composite number? Justify your answer. To check this whether it is a composite number or not, we take the help of fundamental theorem of arithmetic. What does the fundamental theorem of arithmetic says? It says that every composite number can be expressed as the product of prime factors, and that factorization is unique. Suppose if we express this expression as the product of prime numbers, so we can say it is a composite number. So here observe the problem. What we have? 7 into 5 into 3 into 2 plus 3. So in this expression we have two terms. The first term is 7 into 5 into 3 into 2, and the second term is 3. So if we notice, in these two terms we have 3 as common. So let us take out 3 as common. By taking out 3 as common, what we get? So we get 3 into, in bracket, 7 into 5 into 2 plus 1. So here we get 3 into, in bracket we have 7 into 5 into 2 plus 1. Now in bracket, if we simplify that, we get 71. So what we can get finally? 3 into 71. So now here the given expression, that is 7 into 5 into 3 into 2 plus 3, is expressed as the product of 3 into 71, where 3 and 71 are prime numbers. So that means the given expression is expressed as the product of its prime numbers, and we know that every composite number can be expressed as its prime factors. So that means the given expression is composite numbers. So like this, using fundamental theorem of arithmetic, we can explore the properties of real numbers. Let us see one more application. Consider one example, that is example 3, which is given in textbook. Consider the number 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. Now if we observe this problem, here we were given by a number 4 power n, and where n is any natural number. And what we need to do here? We need to check out whether this 4 power n end with the digit 0 for some natural number of n. And here, to verify this, in the place of n, we need to substitute the natural number values, and we need to verify whether we get the end digit 0 or not. But there are infinite natural numbers we have. By placing those values in the place of n and verifying it, it is tedious and never-ending process. So instead of substituting the natural number values in this number, do we have any alternate way to verify this? Yes, the fundamental theorem of arithmetic helps us in doing this. Let us see. So to understand this first, let us consider a number with the end digit 0. So let us do the rough work. Let us take 30. Now in 30 we have the end digit 0. Now let us write this 30 as a product of its primes. So what we get? 30 can be written as 3 into 10, and where 10 is the composite number, so we can further factorize it. We get 3 into 2 into 5, where 2 and 5 are the prime factors of 10. Now observe this prime factorization. In these prime factors, we have 3, 2 and 5. Suppose if 3 is not present there, Now what we have? Just simply we have 2 and 5. Now multiply them, what we get? 2 into 5, that is 10. So what the number we get? 10. And does it end with the digit 0? Yes, 10 is ending with the digit 0. So that means if the 3 is not present in this prime factorization, the number is ending with the digit 0. Now let's suppose, suppose there is 2 is not present. Just simply take 3 and 5. Now what is their product? We get 15. This 15, is it end with the digit 0? No, the end digit is 5. So it is not ending with the digit 0. So when 2 is not present in this prime factorization, the product that we get by multiplying 3 and 5, it is not ending with the digit 0. From this we can understand that the number which should be end with the digit 0, that number should have 2 as the prime factors in its prime factorization. Now again, suppose if 5 is not present there, what will be happen? Suppose let us remove 5 and take 3 and 2 only. Now what is their product? We get 6. Now is it end with the 0? No. In this prime factorization, if 2 and 5 are not present, then the number is not ending with the digit 0. So from this we can understand that in the prime factorization of given number, if 2 and 5 are not present, then that number is not end with the digit 0. So let us apply this concept to this problem. So let us verify it. Now what is the given number here? That is 4 power n. Now for the 4 power n, where n is the natural number, if it should be end with the digit 0, then it must have 2 and 5 in its prime factorization. Now what is the prime factorization of 4 power n? 4 power n can be written as 2 power 2 whole power n, which means 2 power 2n. Now in the base we have only 2 as the prime factor, and there is no 5 in its prime factorization. So since the prime factorization of 4 power n contain only 2 as the prime factor and 5 is not present there, hence we can say 4 power n cannot be end with the digit 0 for any natural number n. So like this, using fundamental theorem of arithmetic, we can explore the properties of real numbers. Now let us see one more application of fundamental theorem of arithmetic. In our earlier classes, we learned how to find the LCM and HCF of given two positive integers using fundamental theorem of arithmetic without realizing it. This method is also called as prime factorization method. Let us recall this process by considering one example. So let us consider two numbers, 24 and 36, and let us write the prime factorization of these two numbers. By writing 24, we get 2 into 2 into 2 into 3, and this can also be written as 2 power 3 into 3 power 1, and the prime factorization of 36 is 2 into 2 into 3 into 3, and this can also be written as 2 power 2 into 3 power 2. Now if we observe these two prime factorizations, in these we have the prime numbers 2 and 3 in common. Now to find the HCF of these two numbers 24 and 36, we need to consider the common prime numbers with their least power. So to find the HCF of given two numbers, the HCF will be find out by taking the product of the common prime factors with their least power. So to find the HCF of given two numbers, we need to consider the product of the smallest power of each common prime factors of the numbers. So again, what we need to consider to find the HCF? We need to take the common prime factors with their least power. Their product will give us the HCF of the given two numbers. Now here if we observe, what are the common prime factors we have in both the numbers? We have 2 and 3 are the common prime factors. Let us consider the common prime factor, that is 2. In first we have 2 power 3. The power is 3 here. And in the second prime factorization we have 2 power 2. Now we need to consider the common prime factor with the smallest power. So here 2 power 3, the power is we have 3, and in the second we have 2 power 2. So where 2 power 2, that is power 2 is the smaller than power 3 here. So we need to take 2 power 2. And also, what is the other common factor in both the factorization? That is 3. And if we observe, in the first factorization we have 3 power 1. In the second factorization we have 3 power 2. Where 3 power 1 has the smallest power. So we need to consider 3 power 1. So now what we get? 2 power 2 into 3 power 1. So by multiplying this we get 12. So where the 12 is the HCF of the given two numbers 24 and 36. So here we need to remember this process, that to find the HCF of the given two integers, we express both the numbers as their prime factorization. After expressing, to find the HCF, we consider the product of the smallest power of the common prime factors of the given numbers. So to find HCF, that is highest common factor, we need to take the smallest powers of common prime factors of each number. Now let us find the LCM. Now to find the LCM, we need to consider the greatest power of each prime factor of the given numbers. Here to find the LCM, we need to take each prime factor which appears in both the numbers with their greatest power. So let us see. In the first factorization we have 2 power 3 into 3 power 1. And in the second factorization we have 2 power 2 into 3 power 2. Now here 2 power 3 we have, and in the second one we have 2 power 2. Out of these two, the 2 power 3 has the greatest power. So hence we need to consider 2 power 3. And then coming to 3, here in the first factorization we have 3 power 1. In the second factorization we have 3 power 2. Since we need to consider the greatest power to find the LCM, so we need to take 3 power 2. So by taking 3 power 2, we get 2 power 3 into 3 power 2. By multiplying these, we get 72 as the LCM. Here we need to remind one important point, that to find the HCF of the given two positive integers using prime factorization method, we need to consider the common prime factors only. But to find the LCM, we need to consider each prime factor. That means to find the LCM, not only we need to consider the common prime factors, but also we need to take the prime factors which are not common. And also we need to remember one more thing, that to find the HCF, we need to take the smallest power of each common prime factor, and to find the LCM, we need to take the greatest power of each prime factor of the given two numbers. So if we remember these things, so we can find the LCM and HCF of given two integers using this prime factorization method. Now we can also understand one more result, that is, so if we multiply LCM and HCF, suppose here consider the first situation. What are the given two numbers? 24 and 36. And what is their HCF? That is 12. And what is their LCM? That is 72. Now let us multiply the LCM and HCF of these two numbers, that is 12 and 72. What is their product? By multiplying 12 and 72, we get 864. Now keep it one side. Now let us multiply the given two numbers, that are 24 and 36. Let us do multiply 24 and 36. What is their product? By multiplying them we get 864. So from this we can notice that the product of the given two numbers, that is 864, is equal to the product of their LCM and HCF, which is equals to 864. So from this we can conclude that we can find one important result, that is the product of given two positive integers is equals to the product of their LCM and HCF. So we can generalize it. So let us suppose the given two positive integers are a and b. Then we can write this result as a into b equals to HCF of a comma b into LCM of a comma b. We can use this result to find the LCM of two positive integers a and b if we have already find the HCF of the two positive integers. That means, suppose if two positive integers are given and we find the HCF of those positive integers, that means we have the two positive integers and their HCF. Now we need to find the LCM. So now in that case, we can use this result to find the LCM. Not only to find the LCM, we can also use this result to find the HCF also when we know the LCM. And also we can use this when we know the LCM and HCF of the two positive integers, and now out of those two positive integers we were given by one integer and the next one is not given. So to find the second number, second positive integer, we can also use this result. So up to now we discussed the fundamental theorem of arithmetic, and also we discussed how the fundamental theorem of arithmetic helps us in exploring the properties of numbers. So using them, now you do the problems which are given in exercise 1.2. So that is your homework. If you get any doubts, post your doubts in comment section.